Welcome to another RDWorks Learning Lab. Today we're going to carry on with our research into lenses and the strange relationship that light and lenses seem to exhibit. Now, I didn't realise this until I started trying to force a very small laser beam through a lens. And there were some strange properties that started to emerge, things that I didn't understand or even know about. I decided I would start investigating lenses in a slightly different way. Now, I've got this rather strange looking lens here, which is basically a large plano convex lens, but it's a good example of something that happens to a lens when it gets larger. You can clearly see that this is part of a sphere. Normally, when you look at our lenses, 20 millimeters diameter, and here's what 20 millimeters diameter looks like. Okay, so we're only looking at the top, this nearly flat section of the lens, when we use a 20 millimeter lens. Now, the fact that this is approximately a 1.5 inch focal length lens, and this is also a 1.5 inch focal length lens, makes no difference. They've still got approximately the same spherical radius on the top here. And what we're going to do, we're going to have a look at how this stuff which is hitting my hand, bright sunlight, can be focused down to do damage to this piece of black paper. We've got the naked 50 millimeter lens here, and we should be able to focus that down at roughly 1.5 inches, and with a bit of luck we should be able to cause some burning. There we go, look. It's even burnt a hole in the paper. I've now blocked it off to a 35 millimeter diameter. Yep, certainly not as much damage there as there was before. Now we'll put a 30 mm occlusion in there. We've still got enough power there to do some burning. A slightly smaller hole. Now we're at 25. Yeah, I'm having to work hard to get it to focus. It's an even smaller hole. Now this is 20 millimeters, which is typically the size of lens that we would use in our machines. Rest that on something so that I can hold that remarkably still and keep focused in the same spot. It's taking a long time, but it does just about burn the surface with a very, very small mark, rather than it hasn't burned a hole in it. This is one of the standard lenses which I've got, which is 18 millimeters diameter. This is a meniscus lens, so it should be a really, really sharp point. However hard I try, but I can't create any damage at all in the area there. So let's remove 15 millimeter diameter from the centre of that 50 millimeter lens and see what happens. 20 millimeters. Wow, 40 mil. Yep, provided we keep it still for long enough, 40 mil works well. This is ridiculous, isn't it? 45 millimeters out of a 50 millimeter lens. That means I've got 2.5 millimeters of the lens only, which is working. And I think I've reached the threshold of stupidity now. Well, that was a nice fun exercise in the sunshine. And of course the sunshine is basically collimated light hitting that lens. It's parallel and it's normal random daylight, and we were able to focus the power of that sunlight with a 50 millimeter lens. And I was able to move it backwards and forwards maybe 4, 5, 6 millimeters, and I was still able to burn a hole in there. We then put discs on the lens. As we put that 35 mil hole on, we got a smaller burn. This picture here doesn't show the remaining tests that I did, where I did the opposite thing. I put a 10 millimeter disc in the centre of the lens, and I kept increasing the size of the disc, the occlusion from the centre of the lens, right up to 45 millimeters. Just before I did the filming, I was able to get just a little teeny weeny puff of smoke if I was to manage to hold the focus in the right place for long enough. So we had 372 square millimeters of area which was focusing the sunlight. Now the sunlight for all these tests was basically a constant because there was no cloud in the sky, and it was done at the same time of the day within a few minutes. And then we did it the other way round, but at 20 millimeters it's interesting that we were just about able to make a mark with 314 square millimeters of sunlight. So I would say, looking at these two numbers here where we had some burning success and just a burning success, there is no difference in the amplification or the magnification effect of the lens, whether I'm using the outer part or the inner part. And that's exactly what we'd expect of a lens. But there is one or two interesting puzzling things here. Look, when we exposed the whole of the lens to sunlight, this huge area, nearly 2,000 square millimetres, we were able to burn a great big hole in it. Ah, yes, I know. That's because I was putting so much power through the lens. No, think about it for a minute. A lens has got a focal point. And a focal point means that all the rays of light are passing through that focal point. Now, that lens was collecting rays right out to 50 millimetres, and it should have focused those 50 millimetres down to something very, very small. That's not very, very small. I couldn't find a very small focal point. Only when I started putting an occlusion on the outside of the lens and reducing the area was I able to start reducing the burn. Now you can download this document, and it's all about this subject called aberration, which is a problem that we have with our spherically shaped lenses. What we've just been looking at with sunlight is white normal light passing through a lens, and if the lens doesn't focus properly to a single focal point, then here's what we get. We get a slightly blurry picture, as opposed to this one here, which has got no spherical aberration. It's a crystal clear picture. Now here's why that picture was blurry. This is a normal lens as part of a 2-inch sphere. The sunlight, for example, comes in parallel like this and hits the lens at all places with exactly the same amount of energy on every one of these rays. With a lens this way round, which is the way that lenses are designed, there are 2 refractions that take place. If we look here, you'll see that that ray is bent just there, and it then gets bent again just there as it comes out of the lens. But the net result is that that ray is focused down to a point a certain distance away from the lens face, and that distance is called the focal point. You'll see that as we move away from the central axis of the lens, and here it is, look, we are 5 millimeters to 15 millimeters away, so that indicates that this is a 30 millimeter diameter lens. The focal distance changes for these rays from 46 down to 41. So there's a 5 millimeter change of focal distance depending on where the rays pass through the lens. That's not how you thought a lens worked, is it? This is what I call a fuzzy focus. We don't have a perfect focus. This is a property that happens with all spherically shaped lenses. So here we've got some strategies for correcting this thing called aberration. Here's our lens, here's our fuzzy focus. And as we start building up compounds here, different types of compounds, we start improving the situation. We get to a triple and then a quadruple, where we've virtually got rid of the aberration. And I already use a compound lens for engraving, which looks like this. Now you'll note I've just said engraving. I need a very, very small focused spot to do photo engraving, and that's what I've created this compound to do. It's very poor at cutting. It seems that what we need for cutting efficiency is we need to exploit the weakness of a lens, this aberration weakness that we get with spherical shaped lenses. So back to that picture there, and we've got our fuzzy focus. But let's just have a look to see what happens when we turn the lens over. Oh dear, what have we done? Light passing through a flat surface suffers no change of direction at all. Only when it hits an angled surface like this one here does it change direction. Okay, so now we are getting a change of direction towards a focal point. As that distance h changes from 5 millimeters to 15 millimeters, we get a change from 48 to 24. That's a 24 millimeter change between that focal point there and that focal point there. This is no longer fuzzy, this is an LSD trip. Now when I turned my big white lens over, I was able to produce a burn, but it was a much smaller burn because all of these rays here were being dissipated, and the only rays that were having any effect were these rays that were coming through the centre here. We was getting a bit of a concentration just here, as you can see, and I was able to produce a small burn because these rays here from the outside were being filtered. So here we've got that same 30mm lens that we've just seen, and we've got our white light passing through here. Now this is a great diagram for showing the way in which these uniform rays of light are gradually combining together with their single intensities to make a much more intense light as it moves towards the focal point. And it also shows the way in which these outer rays have got their own focal point here and are disappearing out into space somewhere and not doing a lot. So this is a great example of why we were able to burn a big hole in our piece of black paper. Look, the intensity of the sunlight was sufficiently strong here that it was able to burn a big hole. Now, is that the focal point? Well, of intensity, that might be the focal point of intensity by the look of it in this diagram. But our light from the laser beam is not the same as white light. White light has got a uniform distribution of energy, but the energy in a laser beam is not uniform. The light intensity at the centre of the beam is significantly higher than the light intensity at the outside, which is 0. Now this is something called a Gaussian distribution, and that's what all laser beams ideally should be like. Now we've also got an arrow here which purports to be the beam diameter that the manufacturer of the tube claims, but as you can see, that beam diameter is not the real beam diameter, because the real beam diameter is out here at 30mm. To all intents and purposes, the light intensity at this outer part of the lens is 0. It's pretty zero-ish for a long way into the lens before we get any sort of change of light intensity. So these are no longer sun rays, these are probably closer to moonlight. We're not going to get a lot of intensification and burning effect from moonlight, but then again, those moonlight rays are effectively out here because of the aberration. So they're not doing much to help us anyway. The only useful part that's coming through this lens is what the manufacturer claims, which is these rays here. Just because we've got a laser beam passing through this lens is not going to change the properties of this lens. This lens is still going to work exactly the same as it did for sunlight. Fuzzy focus. Beams focusing at all sorts of different points, not at a single point. But there is going to be a significant difference in the way in which this lens handles this non-uniform light. This lens has got an axis that passes right through the centre. Now, if we pass a single ray through that point there, there's 0 refraction, because that point there at the top of the hill, at the top of the curve, is flat. It's 0. So it passes through that point with 0 refraction. It hits a flat surface again with 0 refraction and passes right through the lens out to infinity and is never focused. So we start moving away very, very slightly from the axis and we get very high intensity, but we're getting focus, which is, look, these things out here. So these rays, these very intense rays, are not getting focused at a single point. They're getting focused at a range of focal points, which are out here somewhere. And eventually we should get back to these slightly lower intensity rays here, which tend to agglomerate more at a single focal point. With normal uniform light rays, we've got something that I like to call an optical focal point. Now with our non-uniform laser light, things are different. The most intense rays, which are passing through the central part of this lens, where not much focusing is taking place at this point, most of the focusing is taking place at some distance beyond here, and it's not concentrated, it's spread out. So we've got spread out high power beyond the normal focal point. And that produces somewhere a concentration of intensity which I want to call the intensity focal point. It's the point where the conglomeration of intensities can cause the most damage at a single point. Now, although we've got a nice uniform predictable Gaussian shape here coming into the lens, as soon as it starts to move down here, down the beam, what we've got these different types of beam which are aiming for different focal points. This is not an imaging system. If it was an imaging system, we'd expect to see coming out the other side here what we put in, just like a camera, a projector, a microscope. That's an optical system. This is not an optical system. This is an amplification of light energy, light intensity. And this intensity pattern that we've got here is not going to come out the other side of this focal point looking anything like that. We've got the focus of different parts of that beam taking place over a whole range here. The intensity distribution at that point there is not going to be that. Okay, now this is pure conjecture and logic on my part. Hey, I'm not an optical engineer. I've got no scientific equipment to measure what's going on at this point here. So I'm taking the evidence of what I can see, the facts, and I'm trying to reverse engineer how can those facts come about by guessing what's happening in this zone here. Now, all I can tell you is that this zone is not constant, and it's certainly not this. The only reason I can get a different result out of here is if the lens itself is distorting this input information. So let me give you a preview of some of my work, which gives me confidence that what I'm saying is correct. The smallest possible hole, which indicates all the rays are passing through that hole. And that is the point at which I consider to be the intensity focal point. A little test jig that has got water in it. I'm going to burn a hole through this card, and I don't want to burn and get a reflection off of my metal surface. I don't want to possibly set fire to a piece of acrylic by having that underneath. It'll just evaporate, instantly vaporise the water on the surface when the beam hits the surface after it's passed through this piece of card. Hopefully we should be able to see a reflection in the water of what's happening underneath the piece of card. I could just do this. Beep. That's quite a small hole. Yeah, but it's not the proper size hole, because that's only the high intensity part of the beam passing through that piece of card. I'm going to profile what this beam looks like at 40 millimeters as opposed to 50.8. I've now set the beam to be on for 1 second. I mean, that was only about 10 milliseconds to produce that burn, but that's not the real shape of the beam at 40 millimeter focal distance. Here's what the real shape is. Here we go with our 1 second burn. 52.6. I've taken the lens tube out. What we're going to look at now is the raw beam. So what we've just done there is produced a carbon arc, and it's actually quite a dangerous light. There's lots of UVB light and UVC light in that very bright white light, so you don't need to look at it for very long to damage your eyes. Now, you've just seen my tests in real time. I'm now going to take a few moments out to walk through those tests to try and explain exactly what's going on. The first thing we're going to look at in slow motion is the wood burn, because producing carbon is a very interesting process. There's an obvious relationship between the intensity or the damage capability of the beam and exposure time. So if we've got a very short exposure time, we will only be able to see this little teeny-weeny piece of the beam at the top here, because there isn't sufficient time for this part of the beam, the larger, lower intensity part of the beam, to do damage. When we expose the Baltic birch plywood to a raw beam, the initial burn here is very high intensity, and it remains high intensity. And what happens is, as time goes on, the lower the intensity, the longer it takes for it to damage the material. So eventually you'll see the beam getting bigger and bigger and bigger as we allow more and more time. But of course, at the same time as that's happening, we've still got this bit at the top here, which is busy eating into the material and creating a lot of damage. Just for reference, these circles on here are 10 millimeters diameter. So I've just blobbed the maximum intensity there just to find out where my beam is going to hit. You can see that that beam is about, what, 1.5, 2 millimeters diameter in relation to this 10 millimeters. So every frame that we look at is 20 milliseconds different from the previous frame. Okay, so let's step into our first frame. We've got a chemical reaction that's taking place here, and we're producing a massive amount of fumes. Now, it doesn't look like it because you can't see the fumes, other than these flames are the fumes being exploded outwards, and the laser beam itself is busy reheating them and reburning the fumes. Let's step on another 20 milliseconds, and wow, look, all of a sudden those fumes have become heated and have ignited. The very intense light in here caused by these fumes burning is actually causing the camera to stop down, and we can't actually see the detail of what's going on in here. Now we start to watch this spot going black because we've got a very high intense beam at the center which is doing damage, and around the outside here we've given enough time now for the outer part of the beam to start scorching. It's not evaporating, it's actually scorching the material around the outside. There's not enough energy to vaporize the material. If we keep an eye on this black patch here in relation to this 10 millimeter diameter here, you'll see that this is growing frame by frame. The combination of oxygen and carbon at about 900 or 1000 degrees C creates carbon dioxide. Creating carbon dioxide from carbon and oxygen is something called an exothermic reaction. In other words, there's excess energy when we add oxygen and carbon together, and that excess energy will appear as a bright white light here, a carbon arc. And now you can see this carbon arc beginning to develop in the bottom here. All of a sudden you will get a huge brightness here. We're still producing flammable gases here. Now I'm going to step through this fairly quickly because nothing changes, except if you watch this around the outside here, you'll see this is the outer part of the beam that we spoke about, right towards the lower intensity part of the beam, which has now had enough exposure time to start having an effect. And you watch, you'll see that that grey, that black area is growing. The more time we give it, the more we're seeing the full width of the beam. So even though I'm stepping through this quite quickly now, you can see we've still got a little bit of beam growth out here, and now I'm turning off the power. And there's our end result. Now this started off as what we thought would be roughly a 3 millimeter diameter beam, but compare that damage there with this 10 millimeter circle and you'll see we're probably out to 6 millimeters or more. So the beam diameter itself is at least double what the manufacturer claims. But of course you can see the major part of the damage has taken place within roughly a 3 millimeter zone. Now you will remember that I pointed out to you that one of the reasons why I put this hanging over the water bath is so that we could see a reflection in this surface here of what might be happening underneath where we're going to do our burn. Ah, somebody's shining a light on here. Well, that's not a light, that's the beginning of a red glow, the beginning of a scorch. Now 20 milliseconds later, first of all we've got some fumes which are being reheated here by the incoming laser beam. We've got a red glow in here which shows that we're doing some burning inside this hole. I say inside that hole, but what you've got to look at is after 20 milliseconds that beam has pierced its way through 1 millimeter of basically wood pulp. And look what we've got down here. We must be through the material at this point because we can see the light reflected in the surface of what's happening underneath here. I'll step back a frame so that you can see that this is not there one frame earlier. You'll see how quickly that high intensity has vaporized a hole. So let's look at the light in that hole, and let's look at the size of the hole as I step on another 20 milliseconds. Now the light has actually disappeared because we've actually created a hole and there's no more material to vaporize and produce fumes at that moment in time. I'm going to step through the next few frames fairly quickly so that you can see this black hole changing in size. And then all of a sudden something strange starts to happen. The hole is basically a carbon tube. That lower intensity part of the beam is now heating up the carbon tube that's inside that hole. And it's creating this exothermic reaction, the carbon arc. And there it goes. It's almost like an explosion, and we can watch it underneath here. Okay. So we're now going to look at what I think is the intensity focal point for this lens. And that happens to be at 52.6, 2 millimeters beyond the natural optical focal point. Here's our first piece of evidence that something's happening. We can just about see that orange mark on the surface there, if you look very carefully, the orangey red mark, but we're converting some material into fumes. Now I must redefine for you what fumes are. Fumes are not gas. Fumes are solid or liquid microparticles suspended in the air. They're solid particles. They must be solid because the laser beam is hitting them and reheating them. And that's what we can see here. So let's step on another 20 milliseconds. And so those fumes are rapidly expanding upwards and exploding outwards because look how far they've come up. You can see the red glow inside the hole. And you may not see it, but just here, and we'll step back a frame as well, that light disappear. Step forward again and you watch that little dot appear. See it? So we've pierced right through that material in less than 20 milliseconds. But I'm going to step through a few frames very quickly and you can watch that hole grow. Now this hole is growing because we are vaporizing the material away completely and rapidly by the high intensity part of the beam. But we shall eventually get to, in a few frames, there we go, we've got to the mid intensity part of the beam now. So we're now starting to heat the carbon that's on the walls of that hole, and we're going to get our, here it is again, we're going to get our explosion of exothermic reaction as the carbon and the oxygen start to combine. Again, we're passed through that damage capability of the mid zone, and we're still producing a little bit of this exothermic reaction, but the hole size has now reached nearly its full size. That mid energy is now passing right through that hole, and you can see it at the bottom here. We've got the glow from the inside of the hole. And there we go. We're just about at the end of the burn. Now when looked at from the underside, you may well say, well, that's the smallest burn. That must be the focal point at 50.6, 51.6 and 52.6. But when we look on the other side, you compare that 52.6 damage on the surface to the 50.6 focal point damage on the surface there, and you'll see there's a big difference between these two diameters. So we need to go and look at these under the microscope, and I'll show you what I mean as to how this has got to be the focal point and not that one. So this is our burn 4 millimeters above the focal point, and as you can see we've got the hole, which is the central core that's been vaporized away, and then we've got all this carbon around the outside here. if we've got some sort of a symmetry to the burn here, but it clearly shows that we've got a big scorching area here. Now the diameter of that scorch there is roughly about 0.7. So this is the one that I think is the correct focal point, and you can see the difference in the relative size of the vaporized section and the scorched section. There is very little scorching, virtually all of the beam passing through one spot, and we're doing very little in the way of collateral damage from the low intensity beams. They're all passing through this one very small area, which is, yeah, and so instead of 0.7 we're down at about 0.45. Now this burnt card test has already started to indicate two things about a lens specification. This is a 2-inch meniscus lens used the correct way with its meniscus side downwards, which should have a very, very accurate and fine focal point. The spot size should be around 0.08, maybe as much as 0.1, not 0.45. Now the other thing that we've already started to prove is that the focal distance is not what it seems either, because this is supposed to be a 50.8 2-inch lens, and in fact it comes out at 52.6, so that's already 2 millimeters longer than the focal distance specified for the lens. Again, somewhat of a surprise for a meniscus lens. Now this is only one simple example of how to read the data that you're going to see in my following report. Here we've got a 2-inch lens which is being used the wrong way up. And you know what the wrong way up means. It's got an absolutely abysmal aberration. And here we've got the shape and depth of a beam penetration, 30 watts of beam penetration after it's passed through this lens. The focal point was on the surface of the material. We now compare that 2-inch lens with this super focusing 4-inch meniscus lens. Well, let's take a look at two things. Here's exactly the same power, 30 watts. Look at the size, look at the penetration, and look at the shape. The only thing that's changed is the lens. The lens must have done something to the same laser beam to create a different end result. Now, after the last 15 minutes of demonstrating how normal light passes through lenses and how those same lenses treat laser light in a completely different way, let's give you a little bit of background as to what's going to follow. Now, several years ago I installed a 70-watt tube on my machine. The raw beam can damage a piece of 25mm acrylic in the following manner. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now the basic tube spec says that this beam is about 6mm diameter, and it's not far out. Now I've used this beam for doing all sorts of cutting tests with the many lenses that are in my collection. But one of the things that I never managed to discover was how lenses manage to perform the wonderful trick that they do. One of the things that I was able to demonstrate is that I could cut this 26mm thick hardwood with a completely straight edge, as you can see here, with a 2.5-inch gallium arsenide lens using my 70-watt tube that you've just seen me do a mode burn test on. Let's just run it for a second and you'll see what I mean. Okay, it was running very slowly, but it did a super job of cutting through that piece of 26mm hardwood. How and why should it do that when everything that we know about a lens says that the beam beneath the focal point starts to diverge and lose its energy? I mean, that just doesn't make any sense at all. And that set me off on another journey of adventure and discovery. And eventually I discovered what the mechanism was. It's all down to intensity and how you can apply that intensity. Now, I'm not going to go any further than that, but that left me with another interesting problem. I'm lucky enough to have an RF CO2 laser machine as well. It works exactly the same as the glass tube. The only difference is that the CO2 beam is generated by high frequency radio waves as opposed to high voltage electricity. the end result is the same. Bear in mind this is only 30 watts. And so what we're going to do is have a quick look at the mode burn from this machine and compare it with the 70 watt mode burn that you've just seen. 0, 1, 2, 3, 4, 5. So that's how far the beam penetrates in 5 seconds. And it's only about 4 millimeters maybe diameter at the mouth there. So this is doing the same amount of damage in half the time that my 70 watt beam is doing this. I wonder what we can do if we put this beam across to the middle of my machine and then put it through a lens. Because the beam on an RF machine has got a very serious divergence problem, the beam is definitely not parallel. So consequently, the normal approach for operating an RF machine is to use something like this, which they call a beam expander. Now the minimum beam expander that I could use is ×2. In other words, it's likely to change this beam from 4 millimeters maybe to 8 millimeters or 7 millimeters, something like that. 0, 1, 2, 3, 4, 5. So the beam expander is pretty damn useless because all it does, it expands the beam and decreases the intensity, as you've seen on those pictures there. That's not what I'm after. I'm after keeping the high intensity with the small beam. So consequently, I have engineered my own beam expander system here. Here we've got the laser source. It's bouncing off of mirror 1, comes down to mirror 2, and across to mirror 3, and then down to the lens. Well, there's some dead distance here, okay, before it gets to the lens. And that distance is about 480 millimeters. And then I've got to project my beam down onto the table itself, which is 500 by 300 millimeters working area. So basically I've got to work between about 400 millimeters at this corner to 1200 millimeters at this corner to cover all the possible area of the machine with this beam that I'm trying to create. Now I've been told by optical experts that that's a total impossibility. I've got to expand the beam to make it parallel. But I'm afraid my experience with lens theory tells me that laser beams and lens theory don't really go together, and that I should experience and experiment for myself. So after playing with lenses and distances between the lenses using my telescopic beam conditioner, here's what I finished up with. Here's the raw beam that comes out of the tube, and I managed to get an even better beam projected across to the middle of my table at about 800 millimeters from the source. Now at plus or minus 200 millimeters, i.e. at 600 and 1000 millimeters, I was able to get these reasonably matching beam sizes. So in other words, I've got a beam which is at least as good as this for probably 400 millimeters area of my table. And then when I get to the corners of the table, I've got these burns here, which are not as good. They're quite a big diameter, as you can see. The obvious thing that you can see here is that the bigger the diameter, the less the penetration. So we can already see that this is a smaller diameter because we've got a greater penetration. This is a smaller diameter because we've got more penetration than this one. So although it's difficult to assess the size of these from their entry points, we can very quickly see what the entry points is in terms of depth. So this theory of doing a lot more damage in the same period of time if you can keep the beam small was the thing that was driving me on to my experiments that you're going to see me use today. So I've done a huge report which documents all sorts of lenses using these different size beams around my table. So I've got 5 different beams and probably about 15 or 16 different lenses used the correct way and the wrong way to see if I can find the right sort of lens to give me that cutting monster. It wasn't very long before I came across a problem. Keep an eye on these numbers at the top here, because the thing that I'm interested in is finding a cutting monster. I'm not interested in anything here. These are all just happen to be, if you like, means of analysing what's going on. The only thing that I want is a fast cutting speed, and the only way I can determine whether I've got a fast cutting speed is to do a cutting test. This happened to be the fastest cutting test at 20 millimeters a second. Now, just as a reference, I can cut this material on my 70 watt machine at around about 35 millimeters a second. So I'm way off that at the moment. But I've also got a K40 with a 40 watt tube in it, and I can only do about 15 millimeters a second on that at the moment. And yet I'm now able to get 20 millimeters a second out of a 30 watt tube by using a 1-inch lens. Now, you can't see that this is a 1-inch lens because I called this test D, but this is just a 1-inch lens, plano convex, used the correct way up, i.e. the convex side up. The sort of things that I would like you to look at here are the way in which we can see that there is a definite focal point here somewhere around about probably this point here, 12. Okay, and then we've got a little bit more difficult to find a focal point here, but I think it's probably that one at about 13, and that one may be 13 as well, because I also put the numbers across here where I thought the focal point was. We can sort of see where the focal point is. It's not very distinctive for a lens that's a 1-inch lens. I would have expected it to go on from there to there to there and back to there and there again. Very, very distinctive focal point, but it isn't there. Take a look at this and you'll see that there is, can you see a slight growth in the beam there? What I call ballooning. Now, it's more obvious down at this one, but let's just stay with this one because this is our reference one that we're going to look at. This one, the lens has been turned upside down. Look at the completely different shape of that beam. That burn has got more of a trumpet effect to it, and it's got no ballooning. And also, let's take a look here. Can you find a focal point easily? Yeah, it is there, but it's not obvious. The thinner the beam gets, and here we are at 800 with our tall thin beam. Look, you can hardly detect the focal point there. Remember I said about compound lenses and how if you use a compound lens, you should get rid of the aberration. 27 millimeters a second for this one. But this is a very special compound lens, which technically should not be a good cutting lens. And there is another way that I used to check the cutting performance of these lenses, and that is to run a little beam in here, 20 milliseconds long. Now look, here's what that beam shape is after 20 milliseconds, and here's what it develops into after 2 seconds. Now at 20 milliseconds here, look, we've got a much deeper burn, and then we've got a much thinner compared to this one. Look at this, the ballooning on this one. These are by far and the best cutting, and they've got very nice thin curves on them. So now we compare that to, look, this is a 4-inch gallium arsenide lens. It's quite a deep burn. It's a reasonably straight burn. It's a little bit trumpeted. In other words, that gives the impression almost of a mode burn because it's got this very long, thin trumpet shape. Okay, this one here is much straighter. This one here is reasonably straight. But let's just take a look. Look, 9 millimeters a second, 6 millimeters a second. These are rubbish cutting speeds, but look at the size of the beam and the curve that we've produced. And the other thing about it is, look, there is no focal point, and the beam is huge. Now, we've already mentioned this spherical shape here. As the focal length gets longer, so the spherical radius on the lens gets larger, i.e. the lens gets slightly flatter. Okay, and you can see that as we go from 1.5 to 2 to 2.5 to 4. Now, the other thing that's obvious about this as well, as the focal length gets longer, because the beam size is exactly the same for each one of these, although I haven't shown the income beam, the included angle of the beam as it comes down towards a focal point gets less and less and less. Now here we've got drawn roughly to scale, it's a 20 millimeter lens. Now with this 20 millimeter lens, what I've done, I've drawn my 10 millimeter beam on here. It's a 5 millimeter beam which has got 10 millimeter extremity on it. There's the 5 millimeter aspect there. I've drawn a whole load of colours here representing different parts of this intensity profile. here is that Gaussian distribution. Now, Gaussian distributions have got a very interesting property, and that is that this length along the bottom here, let's call it the beam size, 10 millimeters, and here we've got an intensity here. It doesn't matter what that intensity is, it's just an intensity level of some sort. But what we've got underneath here is an area. Now, if I want to regard this as being a 30 watt beam, then that area under there equals 30 watts. It doesn't matter what it is. But when I reduce the beam size, as I have done here, to about 3 millimeters, here it is, reduced to 3 millimeters, what happens is the area under here has still got to remain 30 watts. So this area is exactly the same as that area, but because I've squashed this area down into a much smaller baseline, it's pushed the intensity way up. So although I've reduced this from, say, from 10 to 3, that's approximately a 3 times gain. The height will go up by approximately the same, 3 times. These beams that are close to the centre line are very high intensity, and they will pass through near to the axis of the lens. Now, just because these are close to the centre line and they are pretty flat, as you can see, this area here, then what's going to happen is these rays, although they will focus, the rules of refraction remain the same. It's just that these will focus because of aberration at a point way beyond the nominal focal point. These beams will not collide and produce a definite hard focal point anywhere. They will be spread out, and that's the bad news, because these are close to the centre line, right? And as we get further away from the centre line, this is where the real work will probably take place, because these will tend to focus into one spot. These are nice engraving intensities down here, whereas these are nice cutting intensities if we can exploit them in the right way. Now let's look carefully at what I've done now that I've reduced the beam size to 3 millimeters. Here's my high intensity stuff, and it's even closer to centre line now because I've squashed it down. All of that high intensity power is sitting on a flat spot at the top here nearly, where it's got very little focusing ability. So these rays are likely to focus well beyond what you'd class as the normal focal point for these beams out here. Now, I've already described to you how the aberration has this effect. So these beams are going to go almost right the way through the centre of the lens unaffected, because their focus is going to be so far beyond the nominal focal point, wherever that happens to be, that it's not going to have an effect. And that's one of the reasons why we're getting these big burns and why we're unable to focus this material, because even though we've got our orange rays and our green rays here, look, these orange rays and these green rays are still on a very flat part of the lens. When you look at the results, you can see that the 1-inch lens that I used had got some sort of focusing ability on it, but that was because this radius now is a lot smaller, i.e. the flat spot at the top here is a lot less. And some of these orange rays and these green and yellow rays are able to focus. And so I can see a focus on a very short focus lens. As soon as the lens starts getting longer and longer, all this stuff is disappearing right through the middle of the lens and is being focused way beyond what you class as the normal focal point. That's why it looks as though we've got no focus. Now this stuff out here, which previously we said was a very little value, now if you look, that dead zero area is no longer zero for very long. It starts to come up and become quite powerful. Not very powerful, but quite powerful. And that's the area around here that's doing all that scorching. I found by accident that a compound lens has got some sort of properties which will allow me to exploit these very high intensity rays. Now, I haven't yet worked out what that is, and I've got to do a lot more experimenting with compound lenses because there's some promise there. Now, one of my scorch tests was attempting to find, if you like, this point here, where all the rays are passing through a single point. But what we've got happening here, we've got our powerful rays coming down the centre here, And we've got all these other rays which are mixing with it, but who knows what the shape of the beam intensity profile is. At this point, it's certainly not Gaussian. It's a right muddle, as you can see. But what we're likely to see is this stuff here burning through the centre and this stuff here scorching round the outside. Now, if there is sufficient focus in this beam, then what we should find is that we've got very little halo around a very sharp burn hole. Okay, and that's the whole purpose of my cardboard burn test, to try and profile this beam to see if I can get any information about the relationship about the low power and the high power within the beam. Okay, now let's stop here because I have to remind you of a couple of things. First of all, I'm not a teacher, I'm a student. This subject is something that I have an insatiable thirst to understand. What I'm doing is showing you how I'm going about my discovery process. Here I am, 3 years on, from trying to find out how the mechanism of cutting takes place. And I realised after that experiment that something strange was going on with lenses, because, let me just show you this. Now, who in their right mind would do that to a lens? But that taught me an amazing lesson. There was something about the rays that come through the centre of the lens that causes the cutting action. Prior to my destructive act, that lens could cut 6mm MDF, 6mm acrylic, and easily gobble through 3mm plywood. Now it's abysmal at cutting, but it's still a fantastic engraving lens. Well, I think we've found the answer today to a question that's been bugging me for about 3 years. Why is that hole through the middle so important to cutting? Now, let's be honest. My attempt to produce a cutting monster from a 30-watt machine has been not a complete failure, because I have found with compound lenses that there's something there still to explore. But with standard single lenses, it's an absolute disaster. There is an incompatibility with this very small high intensity diameter and the small diameter at the center of a lens, which is not very good at focusing to a point. It's going to send these high intensity rays way beyond the focal point, where they're not going to do a lot of concentrated damage, as you hope they might do. And that's the lesson that I've learned from this experience: the incompatibility of thin beams with lenses. Now, you can look at all the experiments that I've carried out with different lenses in my report if you're interested in seeing all that detail. Now, I've added a clickable link into the description. That clickable link will get you to a contact form which will enable you to email me privately, and I will send you a copy of this report. So we've got 5 different common beams in my report, and you can take a look through the way in which one of the beams, and you can choose any one of the 5, across all the lenses has a different effect when it comes past the focal point. This clearly demonstrates that a common beam does not give a common result, and that the performance of a beam is not just dependent upon its focal distance. You can have a focal distance with a meniscus lens which performs completely differently to a focal distance from a plano-convex lens or a gallium arsenide lens. So we've got 3 different outcomes from the same beam, and it's all to do with the various aberrations that are occurring with different types of lens. So we don't have a physical focal point, it's a fuzzy focal point. It's not an optical focal point, it's a focal point of intensity, and unlike uniform light rays, where this stuff passing through the middle will be basically unnoticed, it won't have a major effect. Now, every part of these red beams, as I said, is going to be focused, but not at a single point, and that's the fundamental issue here. The fact that these red beams are the most intense beams, they're passing through a section of the lens which is virtually flat, and I've got very, very long focal distances for each one of these rays, and they'll all be slightly different, not at a single point. Because once we start spreading the rays out like this, we start moving around a part of the lens which is capable of doing a better focusing job. And somewhere there is a relationship between the spacing, if you like, or the width of these high intensity rays and their relationship to the curvature of the lens that they're going to pass through. So that brings up the point that there is an efficiency factor, that a single beam will be most efficient for one particular type of lens at cutting. Now, what I've done here, I've destroyed the high intensity part of this beam by making it wider. This is still a 30-watt beam, and it will cut, but not very well, because I've decreased the intensity, and I can't get that intensity back with this lens. However, there is a way to increase that intensity. So we've increased the intensity of these red rays, and they will still pass through the central axis of the lens, but they will be further away, some of them, so that they will be having a much more beneficial effect for cutting, along with these orange rays. These rays down here will very definitely all focus to nearly a single focal point, whereas these rays will just carry on and pass through that hole in the centre of the lens that you saw me with just now. But they will still have some focusing effect because they are not right on that central axis. They are very slightly off the central axis and will start to focus. And it is these rays which are focusing now that are creating the ability to cut deep. Intensity and beam size are very important, but equally important is the geometry of the lens face. The first thing is, when you have more power, you naturally have a bigger beam. That's on a glass tube. You can make the beam whatever size you like with an RF tube, because you can use a beam expander. Because a K40 beam is not much different to this, it's probably a little bit bigger, but look, all the power and intensity is right at the center. So this is a very, very poor cutting lens, because most of that power is passing right through the center and disappearing out to infinity. The only thing that is good on a K40 is probably this little bit of power here for engraving. That's all they originally claimed to be, engraving machines that could cut as a side act. So when we jump up to a more powerful tube, like say a 90-watt tube, as I've displayed just here, here's our 30-watt, here's our 90-watt, but of course the thing about a glass tube is we've got a power control on it, and the power control on a glass tube changes this Gaussian shape. So if we come down to an engraving percentage, which may be only 15 or 20%, then what we've got is an even shallower curve here, like this. So as we get down to say 12 or 15%, the shape of this curve drops to something down here, where the intensity is pretty low. So we've changed the ratio of these intensities as we go across the beam profile. And that's what makes it so much better and easier to work with a glass tube for engraving. We can produce a softer beam. We have control of the beam sharpness with a glass tube. That isn't a luxury that you have with an RF tube. So with an RF tube, yeah, the beam starts off very small, which is not good, as we found out. And so you put it through a beam expander to make it large like this. And as you put it through a beam expander to make it large, what happens is you reduce the intensity and reduce its propensity to cut well. So you can compensate for the weakness of enlarging the beam by increasing the power of an RF machine. So the essence of it is, my 30-watt machine is never going to be a decent cutting machine. It's always going to be maybe an engraving machine that can sort of cut with 30 watts. So if ever you're going out to buy an RF machine that you want to cut, then you're going to have to choose something with a fairly high power laser source. I'm afraid high power laser sources go up exponentially in price. And then you're going to have to ask yourself the question, well, is it better to go for an RF source, or is it better to go back for a much, much, much cheaper glass tube with a high power? So you can clearly see on these different focal length lenses how the angle of the rays are coming in at shallower and shallower angles as the focal length gets longer. The flatter the curve, i.e. the geometry of that top surface, determines how steep these lines will converge on the axis. And these red lines are converging at a much slower rate, i.e. they will focus at a point much further in front of the nominal focal point than these will, because these rays are coming in at a much steeper angle, and they will tend to focus maybe down here. So their ability to cut is a lot less than the ability of a 4-inch lens. But of course a 4-inch lens needs power. A more powerful tube will have a wider beam, and it will have a much higher intensity within that beam than what I'm trying to achieve with my narrow 30-watt beam. So that answers a question that's been kicking around in my mind for many years. What is it that makes an efficient deep cutting lens? I know that my 2.5-inch gallium arsenide lens cuts much better than a 4-inch lens. And I did investigate why. And the answer is because of the different refractive index of the material. The actual radius on the top of a 2.5-inch gallium arsenide is flatter than that on a 4-inch zinc selenide lens. And so consequently it's able to cut deeper, faster than a 4-inch zinc selenide lens on my particular beam. Now that might not apply, as I can now understand, to everybody's beam. It really depends on the shape and the intensity pattern within your beam. So the beam itself is a very important factor, and the intensity within the beam is a very important factor. So the final summary that I have to come up with is where I thought I was at the beginning. There is no such thing as a focal point, because the optical focal point is an optical focal point, not a focal point of intensity. The focal point of intensity depends on the shape of the beam and the style of the beam and the focal length of the beam. And as you've seen, there is no such thing as a depth of field. Depth of field is the sort of stuff that's used in cameras and optical technology. It's not something that can be applied to laser beams. And finally, the magical thing called spot size doesn't exist, as I've shown you with that white light. We can produce a huge hole from something that's got a very, very short focal point and supposedly a very, very small optical spot size. So everything that we know about lenses is basically suspect. It's about right, but certainly we get away with it because we don't work to the extremes that I've been looking at with my experiments. So although this project was doomed to failure, in fact it's been a great success because it's answered and tidied up so many loose ends that have accumulated over the past few years. I've been doing something that is unlikely that anybody else will be doing, which is messing around with a very narrow beam. But it's taught me a great deal about lenses and their weaknesses, laser beams and their weaknesses. Used in the normal way, which most people do, you will never see these problems. Thank you very much for your patience and time. Who knows what my output rate will be in future, because there can't be many more problems for me to investigate.